Hey everyone, it's Mrs. Fellon. I am on lesson 5.2 on page 130 of your student journals. And today we're going to talk a little bit more about simplifying with rational exponents and kind of using radical form as well as exponent form. All right, so there's some things I wanted to kind of go over. And just as a quick reminder, is what we talked about in the last video, is that a rational exponent is an exponent with a power that's a fraction. So like, for example, 5 to the 1/2. And its equivalent form would be to write it as a radical. So like a power of 1/2 is the same thing as saying a root of 2. So in other words, a square root is the same as raising something to the 1/2. Just like the 4th root of something is the same thing as raising it to the 1/3. And then even if we get a little fancier and we kind of raise something to the 2/3, remember that the 2 is the power and the 3 is the root. So if I was going to write it as a radical, I would write it like that. All right, so basically there are names for all of these properties, and that's what they're kind of getting at here. Some of the big things, the rules that I want you to know, and just these are just kind of like standard rules for when we're simplifying rational exponents or any exponents for that matter. We want to make sure that we have, so I'm going to write this down, so no perfect nth powers. So what that means is if you had, like, say, in your expression, if you're simplifying an expression and let's say you had the answer the cube root of 8x or something, you would need to reduce the cube root of 8 because the cube root of 8 is a perfect nth power. All right, so you want to make sure that you are reducing all perfect nth powers. The other rule is that we're not going to have any radicals in our denominator. So in this one, what we're looking for is that we're not going to have any, like, kind of like how we talked about before with when you probably did this in Algebra 1, like rationalizing your denominator. Same kind of deal. You're going to have no radicals in the bottom of your fraction, and that's kind of what we're going to get at. All right, so there's some words here. Simplest form of a radical just means that we're going to reduce it. A conjugate. I'll show you what I mean by a conjugate, and then when we talk about like radicals, that means two radicals that have the same radicand. So for example, 3 root 2, and if I wanted to do 5 root 2, because these two radicals are the same, we'd consider them like radicals. All right, so we have all these properties, right? Power of products, or product of powers, power of a power, and so forth. And so what I want to do is I think it's a good idea for you to kind of review some of this stuff, right? So to look over these certain rules that we have here. And we have, for example, if I multiply two a's, or if I multiply two values, that's something that has the same base. If I multiply them together, I can add their exponents. So this is kind of the generic version of the rule, and this is if you put it with numbers. So for example, if I had 5 to the 1/2 times 5 to the 3/2, because they both have a base of 5, we could add their exponents together. So 1/2 plus 3/2 would give me 2, so that'd be 5 to the 2nd power, or in other words, 25. Same thing with power to a power. Again, all you're really doing is multiplying your exponents. When you have a power on the outside of a parenthesis, you just have to remember to apply that power to everything inside. When you have a negative power, we want to get rid of our negative exponents. That should actually be another rule that I'm going to put up here. So no negative exponents. And that kind of holds true for any time we're doing simplifying of radicals, right? Or any kind of exponents for that matter. Anyways, you're going to get rid of the negative exponent and then reduce. A 0 power, remember that still holds true. Anything to the 0 power is still 1, whether it's no matter what it is. Remember the rule when you subtract exponents. So if you have the same base and you're dividing like 4 to the 5/2 over 4 to the 1/2, you are subtracting your exponents here. And so again, you're subtracting fractions, so you might have to find a common denominator at times. But again, you're keeping the same base and you're just subtracting the exponents. Same thing up here when you added your exponents. You're keeping the same base and you're adding your exponents. And then here's a fraction raised to a power, and just remember that that power kind of goes to everything inside that fraction. All right, we're going to jump around a little bit. So I need you to move to page 128. So we're kind of going backwards here. Let me find 128. All right, so this is kind of just doing a little matching, and I just wanted to go over all of these powers again, just with you. So it says a to the negative 2. How you would be expected to write that is 1 over a squared. And the reason why is because we don't want negative exponents. Here's the power. It's something in parentheses raised to a power. So it's a to the 4th, b to the 4th, because you apply it to both. And then here's the power to a power, so you would multiply those together. So you'd get a to the 12th. On this one, since they have the same base, you would add your exponents. So you would have a to the 7th. On this one, you would apply that power to both numerator and denominator. So you'd have a cubed over b cubed. And then on this one, because they have the same base, you can subtract your exponents. So you'd have a to the 4th. And then anything to the 0 power is 1. All right, so let's try some of these in action, right? So let's give a few of these. I'm not going to do them all, but we're going to do some. So let's start with letter A down here at the bottom. And I'll do A, C, and E with you, and then you guys can do the rest. So notice that they have the same base. So what you're going to do is any two things that have the same base, you are going to add your exponents together. So I would do 5 to the 2/3 plus 4/3. So again, all I'm doing here is adding my exponents together. Because 5 and 5 have the same base, I can add those two exponents together. So I'd get 5 to the 6/3, which is also called 5 squared, which is also called 25. So again, you just want to simplify it down as completely as possible. All right, on this one, this is a power to a power. So remember, on this one, you are multiplying your exponents together. So 2/3 times 3. Remember, when you multiply fractions, you are multiplying across the top, multiplying across the bottom. So you'd have 6/3, or in other words, 2. So 4 squared is 16. And then letter E, if you notice, they both have the same base, so 8 and 8, and they're being divided, so you would subtract your exponents. So 5 halves minus 1 half would give me 8 to the 4 halves, or in other words, 8 squared, or in other words, 64. All right, so let's try some more. I think it's a good idea if we kind of keep practicing. So I'd like us to turn to page 129. And let's do a few of these together. So now what we're getting at is a little bit, so there's a ton of different examples I can do. So I'm trying to kind of hit a variety of examples for us to kind of go through. So on this one, notice that they're both in radicals. So if you were to be, in order for you to multiply these two radicals together, because they have the same the same root, like the cube root of 5 and the cube root of 8, or cube root of 25, you can put this under one radical. So in other words, this could be the cube root of 5 times 25. Or in other words, the cube root of 125. And then if you know the cube root of 125 is 5. All right, letter E. So notice that they both have the same root. So the 4th root and the 4th root. So you can write this as one fraction. Next, I would probably, if you can, maybe reduce that, right? So 4 over 1,024. Actually, 4 does go into that over 1 over 256. So then, if it's a fraction, you can 4th root the top and then 4th root the bottom. So remember, you kind of the same idea as if you had square roots. You can kind of treat it the same way. So the 4th root of 1 is 1, and the 4th root of 256. So what number multiplied by itself 4 times equals 256? And that answer is 4. If you didn't know that one, you could put that one into your calculator. All right, letter A. We're on number 5. So on letter A, what we're looking at is we have two different radicals. Let me scooch this down here a bit. You have two different radicals, and even though they have, they're two different numbers but the same radical, right? So they're both square roots. Notice there's no number in there. When there's no number in there, it means that we are just assuming that it's a square root. So we could do the same thing. We could do 27 times 6, right? And so I could do the square root of 27 times 6 is 162. 162 is not a perfect square. So this is where you have to start reducing your radicals. So what I mean by that is you are going to go ahead and you're looking for a perfect square. So you're looking at numbers that multiply together to give me 162. And so I found 2 times 81. And so square root of 81 is 9, so I can call this 9 root 2. Actually, let me go over letter B. I think it'll be a good idea to kind of talk about this one as well. So if you notice on this one, they both have cube roots, right? So we can write this as one value. So the cube root of 240 over 15. And then 240, if I divide that by 15, I think I get 16. So this becomes the cube root of 16. So the 16 is not a perfect cube. Let me show you how you would reduce this. So I have 2 and 8, right? Because you're looking for a perfect cube, you're looking for 3 of the same number. If you recognize that 8's a perfect cube, you can circle this one and say, okay, the cube root of 8 is 2, and I'm left over with 2 underneath. This is how you reduce that radical. If you did not recognize that 8 was a perfect cube, okay, so let's say maybe that was not something that you recognized, and let's say you kept breaking this down. What you're looking for here is, we call this the prime factorization, right? We have this all broken down. Because you're looking for cube root, you're looking for 3 of the same number. If you're looking for fourth root, you're looking for 4 of the same number. So in this case, I had 3 2s, that's why that gave me a perfect cube, so that's why that goes on the outside, and this 2 that was left over goes underneath. Okay, now we're going to switch back to page 131. So I wanted to go over a few more examples with you. So let's do 1, 3, and 4. Let's try those. Maybe we'll even do 5. All right. So I'm providing some extra practice, obviously on big ideas, but also on my Canvas page, I have extra practice if you're interested in some of this stuff. All right, so this gets into a little bit of a combo problem. So notice you have a negative exponent here. So generally my first rule of thumb is to make these all positive. So all I'm going to do is I'm going to move this to the bottom of a fraction because I'm making that a positive exponent. Now I'm going to apply this power to both of those exponents inside. So when you have a power to a power, you multiply. So 2 to the 3rd power raised to the 1/3. 3 to the 1/3 is 1. And then 3 to the 3rd power to the 1/3, again, 3 to the 1/3 power is 1. So this just becomes 1 over 6. And that's how you'd reduce that lovely problem. Let's try number 3. So first and foremost, notice that 52 to the 5th and 4 to the 5th, notice they have both the same power. So you can actually reduce these because 52 over 4 to the 5th, like you can think of it like that. And 52 is divisible by 4. So 52 over 4 is actually 13. So that's what I'm gonna replace that with. So 52 to the 5th over 4 to the 5th is 13 to the 5th. But then we're also raising it to the 1/6 power. So again, power to a power, you multiply these together. So you get 13 to the 5/6. All right, let's try number 4. So this one is a little interesting because these are all perfect how do I word this? These are all cube roots. Do you see that they're all cube roots? Remember, in a fraction, it's the bottom number, the denominator, that's your root. So this is the cube root of 3, this is the cube root of 27 squared, this is the cube root of 8 to the 4th. So you may want to write it like this, if it's helpful to you. That's an equivalent way of doing that problem. All right, so all of these are raised to the, or have the same root. So in a way, what we could do is we could kind of simplify this. These are all raised to the 1/3. So we can kind of simplify all of this that's in here and then raise it to the 1/3. 27 squared, let's see what 27 squared is. So 27 squared is 729 times 3 is 2,187, and then 8 to the 4th is 4,096. And then if you raise each of those to the 1/3 power, so 2,187 to the 1/3 and 4,096 to the 1/3, so let's do that. 2,187 raised to the 1/3, I get, I actually don't get a real nice number. Let's see here, what else do I have? Well, I guess I could leave this, let's see here, 4,096, let's see if that's a perfect cube. It is. So we can go 2,187 to the 1/3 over, and then 4,096 to the 1/3 is 16. So we can leave our final, it's a little ugly, but we can leave our final answer in this form. So all of these problems, as you notice, they're all a little bit different, but they all kind of have the same, we're using the same set of properties. It's just a matter of kind of getting comfortable, which is why I'm giving you guys some extra practice, just because some of you I think will click, this will make a lot of sense and it'll just kind of click, and then some of you will just need some extra practice with this skill. And so that's kind of what I'm hoping, that by providing you with that extra practice, you'll have the ability to kind of do as much as you need. All right, let's do number 5. It says find simplified expressions for the perimeter and area. All right, so first of all, let's talk about a perimeter. So first, I notice that this is a square. How do I know it's a square? Well, first, all 4 sides are marked as congruent and all 4 right angles. So that tells me it's a square. So in a perimeter, we add up all lengths all the way around. So since they're all the same, I'm going to do 4 times 10 to the 1/4. So that's my perimeter. So let's redo this, all right? If I'm multiplying 4 times 10 to the 1/4, there's no powers going on here. I'm just literally multiplying this by 4. So I get 40 times x to the 1/4, because I'm multiplying 4 times 10, and then there's no other x's, so that would be my, I guess, simplified version. Let's area. So if you remember, for a square, the area would be take your side, so 10 to the 1/4, and square it. So now this one, you have to remember that you're applying this power to both the 10 and the x to the 1/4. So 10 squared is 100. X to the 1/4 squared, you would multiply the 1/4 and the 2 to get x to the 2/4, or in other words, 1/2. So this would be your simplified version for your area. Okay, let's try some more. Let's now move on to page 132. So again, I'm not going to do all of them on here because I want to give you guys, I'm going to save some for you guys to practice, but we're going to do a few of these. So let's try number 6, 9, 10. I'll do 11, 14, and 16. I'm going to do a bunch of these just because some of these get a little tricky. All right, so the 6th root of 25 times the 6th root of 625. So this would be the 6th root of 25 times 625. So one of the ways I think about this is rather than multiplying this together and then have to break it apart again. So ultimately what I'm going to try to do is I'm going to try to simplify this radical. So rather than do that, since this, I'm just going to kind of break it apart when it's in this stage, because this is a lot easier for me than to have to multiply those two numbers together. So remember, 625 is a perfect square, so it's 25 and 25. So I'm going to break that down. So what I have here is, if I break all of this down, I have 25 breaks down into 5 and 5, 625 breaks down into 5, 5, 5, and 5. I'm looking for a sixth root, which means I need 6 of the same number. Well, guess what? I have 6 5s here. This is a perfect sixth root. So 5 goes on the outside. Since there's nothing left over, then 5 is my most simplified answer. Let's try number 10. Number 10 says the cube root of 5/9. All right, so this one gets a little trickier. So we're going to take the cube root of the numerator and the cube root of the denominator. Remember our rule, we can't have a radical on the bottom of our fraction. The cube root of 9 is not a perfect cube. What I know is that 9 is actually 3 times 3, okay? And so in order to make it a perfect cube, what I need is, I already have 2 3s. I need 1 more 3 to make it a perfect cube. So if I multiplied cube root of 9 by cube root of 3, I would get that to be a perfect cube. And so in order to not change the value of my problem, I'm going to multiply the numerator by that. So let me show you what this looks like. So I said that there were 2 3s here, because that's what 9 and 9 is. I need 1 more 3 to make this a perfect cube. So then the numerator becomes the cube root of 15. The denominator would be the cube root of 27, which we all know is 3. And that's why I do it this way. That's why I'm multiplying this by the cube root of 3, so that this becomes a perfect cube, which remembered was the cube root of 27, which then gave me that perfect cube of 3. All right, let's try number 9. I skipped this one for some reason, but let's go back. This is one where, kind of like the one we did up here, where we're going to kind of reduce it, but we're looking for 7 of the same number. So let's think of, let's think of a number that goes with 384. All right, let's try 16. I got 16 and 24. 16, I'm going to do 4 and 4, and 24, I'm going to do 4 and 6. So 2 and 2, and 2 and 2, and 2 and 2, and 6 is 2 and 3. I'm looking for 7 of the same number. So 1, 2, 3, 4, 5, 6, 7. Guess what? There are 7 2s right here. The reason I want 7 of the same number is because I'm looking for the 7th root. So I would simplify this to 2, because that's a perfect 7th root. And I have the 7th root of 3 left over. Don't forget about that little 7 in there. That's important, because if you omit it, that means it's a square root, which is a completely different problem. All right, let's try number 11. On the very first part of this video, I talked about a conjugate, or I said the word conjugate. This is where the conjugate is going to come into play. So 1 over 4 minus root 5. In order for us to get rid of a binomial expression, so that means a binomial, 2 terms, an expression means it's being being added or subtracted. So there's 2 terms being added or subtracted. In order to get that radical off the bottom of my fraction, I have to multiply by what they call the conjugate. So the conjugate is simply the same binomial, like same terms, with the only exception is that it's the opposite sign. So if this was a minus, this is a plus. The reason we do this is that same reason we did difference of squares. If you remember, if I had x minus 5 times x plus 5, if I FOILed this out, right, I get my middle terms to cancel out. So in order for my middle terms to cancel out, I need to have the same values, the same terms, just one sign be positive, one sign be negative. And that's ultimately the same kind of justification as to what we're doing here. So to get rid of a binomial expression, you have to multiply by the conjugate. So I like to put it in parentheses because I don't want you to forget that you're FOILing here. So multiply across the top. Well, if you're multiplying by 1, that's not a big deal. Multiply across the bottom. Your middle terms definitely have to cancel out. So the shortcut way of doing this is always just, since your middle terms are canceling out, all you need to do is multiply your first 2 terms and your last 2 terms. So 4 and 4 is 16. Negative root 5 and negative 5 is negative root 25. Or in other words, 5, right? So that'd be 16 minus 5, which would give me 11. So this is my simplified version. I'm leaving number 12 for you guys to try because I really think that you could practice this. And there's more conjugates. I could get you guys some more practice with that, or you could always just go to like Khan Academy or something. But there's some good that's definitely a skill I want you to practice. All right, last two problems that we're going to go over, which are 14 and 16. So I know this video is getting a little long, so I apologize. There's just a lot of stuff to kind of get through. On this one, this get a little complicated. And so what I want us to do first is I want us to kind of think about how we can subtract or add these together. So because they have the same, because these are both fourth roots, but we're subtracting them, we cannot just put these together unless they have the same value underneath your radical. So what I'm going to do is I'm going to go ahead and start reducing 1,250 to the 1/4 power. So I'm going to do this like we did up here with the root 7, right? So I'm going to break this up because it's just the fourth root of 1,250. All right, so I'll do 2 and then 625. Well, we already did 625 if you remember. The fourth root of 625 is 2. Right. So, wait, no, I'm sorry, it's 5. The sixth root of 220 is 625. So if I did 625 and raised it to the 1/4, I would get 5. That's what I got for that one. So it's a perfect fourth root. So this reduces to 5 and then the fourth root of 2. So that's what this whole thing, or this part of it at least, reduces. Now I'm going to multiply by that 2 that's on the outside. So I get 10 fourth roots of 2. All right, minus, so now we're going to do this other side. So now I have 5 fourth roots of 32. So the fourth root of 32, so I could do, again, I could do 2 and 16 because 32 is not a perfect fourth root. But 16 is, right? Isn't 2 times 2 times 2 times 2, 16, right? So 16 is a perfect fourth root. So we have the 5, and I could write this as 2 fourth roots of 2, or in other words, 10 fourth roots of 2. All right, so now let's bring this back up together. So I have 10 fourth root of 2 minus 10 fourth roots of 2. So because these are the exact same radical, whoops, I'm off the page here. Because these are the exact same radical, right? They both have the fourth root of 2, the fourth root of 2. I can subtract these. And as you notice, these are the exact same. So if I subtract them, I get 0. All right, one more challenging problem. Let's do number 16. I thought that one looked a little crazy, so I thought it'd be good to kind of go over that one together. All right, so the first thing I did is, you notice there's some negative exponents here. I'm going to rework all of this and put everything back to, I'm going to put them all in the same format. So whether it's radicals or rational exponents, and I'm also going to get rid of my negative exponents. So I'm going to move this 7 to the 1 up to the top, and I'm going to move this x to the negative 3/2 to the bottom, and I'm going to move this y to the negative 1/2 to the top. So that becomes that. I'm going to rewrite this square root of y as y to the 1/2, just so it's in the same format as the rest of them. So I got to bump this one to the bottom, and I bumped those two to the top. So now I have x to the 3/2, and then I have x to the 1/2, because I'm going to rewrite that as and then I have z. All right, so I rewrote all of my radicals in the same format. So I'm going to use rational exponents for this one. You could use radicals, but I'm going to use rational exponents. And then I also got rid of all my negative exponents. So let's kind of put some stuff together. So first of all, 21 times 7. Let's do that first. So that's 147. And then, all right, let's see what I can reduce. Y to the 1/2 and y to the 1/2. Well, if I have the same base, I can add my exponents. And 1/2 times 1/2 is 1. And then I have z to the 5/2, okay? I can put together these two x's because, again, x to the 3/2 and x to the 1/2, because they have the same base, I can add my powers. So 3/2 plus 1/2 is 4/2, or in other words, 2. All right, notice that I have two z's in my problem. I don't really like that. Normally, when I look at an expression, I want to have one of every kind of term. So if I have one number, one letter y, one letter x, one letter z. So I want to simplify these two things right here. So think about what power this z has to be. In this case, this is z to the first power, but instead of calling it z to the 1, I'm going to call it z to the 2/2 because it has I want to have the same like denominator. So I'm going to reduce this to 147 y, and then if I subtract these exponents, I get z to the 3/2 over x squared. Okay, I know that these get a little challenging, so I encourage you to practice, and come to me with questions, right? So in class, let's go over some additional problems if you feel like you need it. Sorry about the length of this video. Hopefully you got some good practice out of this, and come to class with questions. See you next time.